So I'll be talking about a recent project done in collaboration with researchers at Boehringer Ingelheim, and it addresses a problem in ground state preparation of many-body quantum systems, which is the Vleck Catastrophe, and we show how to use a divide and conquer strategy to circumvent it in certain cases. Okay, so maybe just a brief motivation for ground state preparation, why we care. Right, so the task is, given a Hamiltonian H, you want to find the eigenstate associated with the lowest eigenvalue. And this is a very ubiquitous problem in quantum chemistry and material science and beyond, just to name a few examples. These, right, if you want to study, say, nitrogen fixation, or you're interested in building better battery cathodes, one way or another, the ground state preparation problem will pop up. And most quantum algorithms for ground state preparation, as we also heard in the previous talk, require that you have access to a good initial state, ideally one that has overlap that scales at least like 1 over poly n, where n is the system size. And the question, of course, is how do you get a good initial state? And oftentimes, you might be able to prepare a good initial state for, say, smaller subsystems of the entire system. Say if you're interested in preparing the ground state of a bunch of interacting molecules, you might have a good initial state for the small parts, for the single molecules. But if you're interested in the ground state of the whole system of interacting molecules, this is less clear. And this is exactly what leads to the Vleck Catastrophe. So to explain this in a bit more detail, let's consider two quantum states, psi and psi star. Psi star is our target state. And assume that there's some parameter delta between 0 and 1, such that the overlap between our initial state, which is psi, and the target state is 1 minus delta. And let's now consider the overlap between the tensor product of n copies of each state. Right? And a simple calculation reveals that this overlap decays exponentially with the number of copies. Now, if you just simply use that result and plug it into, say, a quantum phase estimation algorithm, you'll see, oh, the query complexity, right, because it scales inversely with the overlap, it seems to suggest that for this simple example, all of a sudden the cost is exponential in n. Of course, in this example, this is actually not what's happening, because you would never use the quantum algorithm in that way to prepare the ground state of n tensor copies, because it's n, they're non-interacting, right? So what you would do in this case actually is you would just prepare each copy of psi star individually. And the cost for doing that would only scale like polynomially in n rather than exponential. Basically, what you would be doing is, right, you would just be doing the ground state preparation in parallel on all of the n copies. The question now is if we can use a similar strategy also for interacting systems, where now we don't actually have this tensor product structure anymore. And we show that under certain assumptions, this can indeed be done using a similar strategy. OK. So let me move on to the main result. I'll just state it informally for now, and then if we have time, I can dive into the more formal statement later on. So again, under certain assumptions that I will specify later, on the structure of the Hamiltonian, briefly, it's sort of, you can think of it as related to the entanglement structure of the Hamiltonian in a certain way. And assuming that our Hamiltonian satisfies these properties, then we can show that we can prepare the ground state of n interacting quantum systems using a number of gates that scales quasi-polynomially. So in the best case scenario, we can show that it scales like n to the log n and then some poly n factor. Whereas, right, for the Vleck catastrophe, you would expect a scaling that scales like, say, 2 to the n. And the main strategy is as follows. What we do is similar to the non-interacting case that I just showed you before. You prepare the ground states of the individual subsystems, and then you use phase estimation in parallel to project onto the ground state of pairs of subsystems. So we're using this sort of binary tree structure, and that I will also discuss in more detail later on. And then we basically just repeat this. We keep applying phase estimation in this measure and repeat until success manner to project onto the ground states of an increasingly larger sets of subsystems until we've rebuilt the full ground state of the entire system. OK. And let's dive a bit into the details of our input model in order to explain what exactly the assumptions are that are needed in order to show the quasi-polynomial runtime. So we consider a system composed of n basic subsystems, and for simplicity, let's assume it's a power of 2, so 2 to the p, where p is some integer. And we assume that the interactions between multiple subsystems follow a tree-like structure. I mean, you can always decompose it like that, but it might not always be helpful. But so we're assuming we have this binary tree structure, and our Hamiltonian is we decompose our Hamiltonian in the following form. So the first sum runs over the layers of the binary tree. So in this case, p would be equal to 2. And the root node is n equal to 0, and then the leaf nodes are just level p. And then basically for each layer, we have a certain number of interaction terms, which I label AS here. Right, and S, these are the strings labeling the nodes, and note that S are bit strings of varying length. So for this example, we would say that at the leaf nodes, which form our basic subsystems, say the individual molecules, right, we have terms going from A00 all the way up to A11. And then at the next level, A0 encodes the interactions between the subsystems of its child nodes. And we also define subset Hamiltonians, which are basically just the Hamiltonians of the child nodes, which are basically the non-interacting subsystems that we consider, plus the interaction term AS between the two child nodes. So for the leaf nodes, I mean, this is just the base case. So the subset Hamiltonian is the same as just the interaction term. And then at the next level, for example, in this case, H0 now consists of all the terms here. So H0 is the sum of A00, A01, and A0, and similar on the right side of the binary tree. And then the full system, oops, sorry. Okay, anyway. And the full system is then all the nodes. And just to give you an example, a small example would be just a transfer fit Ising model, 1D, with 4 spins. And in that case, right, so the leaf nodes would just be the single spins, say. And the leaf node terms are just the non-interacting terms, so just the sigma z's, say, on all the individual spins. At the next level, the A0 terms would now encode the interactions between, say, the leftmost nodes, so spins 0 and 1, and then also spins 2 and 3, but we don't yet include the interaction between these two spins. And then the last layer, the term in A star, would then encode the interactions between these two spins. Okay. And so for our access models, again, this is just from the previous slide, this binary tree decomposition. What we assume is that we have access to the following set of oracles. We assume we have access to oracles that prepare the ground states of the non-interacting subsystems, so basically prepare the ground state of the leaf nodes. And then we also assume that we have access to these unitaries, which effectively encode like short time evolutions of these subset Hamiltonians HS, and these will be used for the phase estimation circuit. Okay, and let's now move on to some more details on the construction. So again, we have S is just some bit string labeling a certain node corresponding to a certain set of subsystems, and let psi S be the ground state associated with that subset Hamiltonian. And then similarly, we have that psi S0, and this is really meant to be read as a string concatenation. So you have psi S0 and psi S1 are then the ground states of the child nodes of that Hamiltonian HS. And so this is the key assumption that we make. In our work, we assume that there exists some parameter R, such that for any subset of subsystems, this overlap, which is basically the overlap of the tensor product of the non-interacting states with the target ground state, that is lower bounded by this parameter R. R. And the question then is, of course, how does R scale with system size? And that will tell us whether we can achieve quasi-polynomial runtime or not. And then what we do is, right, for, as I mentioned earlier, for a given string S, we apply phase estimation with the corresponding subset Hamiltonian HS to the tensor product state, psi S0, psi S1. Right, this is our input state here in the phase estimation circuit. And then you just measure the phase estimation register, and if you succeed, you move on. If you fail, you have to repeat it again. So it's very much an incoherent process. We keep measuring all the time. But the thing is, the key point is that if we fail, we only have to re-prepare the ground states of this branch of the binary tree where we failed. So we don't have to re-prepare the entire ground state over and over again, only for the small portions of the binary tree where we had a failure. And that basically allows us to circumvent the exponential scaling in certain cases. Okay. Now for the main result. This is a lot of text, but the key point is if we just look at the query complexity. So this is the query complexity for these the V oracles, which are again the oracles that prepare the ground states of the leaf nodes. We can see that it scales like n, and then there's a bunch of stuff in the exponent. Notably, there's this R parameter again, which sort of dictates lower bounds the overlap between the ground state in adjacent layers. And depending on how R scales, this whole expression can be quasi-polynomial in n. And then there are also some factors. Delta is a success probability, and then we also have a log n factor, which also comes about from the success probability, because as you go up the tree, you kind of need to make sure that you basically project onto the correct ground states with high enough success probability, and that scales like log n. And similarly, like the number of queries you need to these US oracles has a very similar factor, but because you use it in the quantum phase estimation subroutine, right, you have this additional resolution factor here, which scales like H max, which is an upper bound on the norm of any of these subset Hamiltonians, divided by the minimum spectral gap of any of these subset Hamiltonians. Okay. And so just to summarize, what are sufficient conditions for ensuring a quasi-polynomial runtime? So of course, everything on the previous slide was stated in terms of oracles. So in order to actually ensure that we have a quasi-polynomial runtime in terms of, like, say, gate complexity, we require that the ground states of the non-interacting subsystems can be prepared in poly n time. Of course, the evolution operators also need to be implementable in poly n time. This ratio, this resolution parameter, also needs to be needs to scale like poly n. And then the key point, again, the key quantity is this parameter r, which needs to scale like 1 over poly n. Ideally, in the best case scenario, r is constant. And I guess I have enough time to briefly discuss what are sufficient conditions on this r parameter to make this whole thing work. So again, this is the setup from before, our Hamiltonian in this binary tree decomposition. And what we do is we show using perturbation theory that the overlap between the tensor product of the child nodes and the actual ground state that we care about is lower bounded by this expression. And the key point here is that, maybe I should show this, is this ratio of gamma tilde, which is the spectral gap of the Hamiltonians of the child nodes, divided by the norm of the new interaction term. And basically, we need to ensure that this ratio isn't too small. Okay, I can move through that pretty quickly, I guess. The key point is you can derive a recursion relation on the spectral norm of the interaction terms of all these on these AS terms. And if they satisfy a certain relation related to the minimum spectral gap, then you can show that this R parameter is constant, which then ensures a quasi-polynomial runtime. And maybe just to give slightly more intuition for this relation, so what it basically says that the strength of the interaction as you go up in the tree needs to decrease quadratically at least. If it decays faster, even better. But it needs to decay quadratically as a function of the level of the tree that you're in. OK. And then I also have some numerics. Again, we're looking at this transfer fleet Ising model for simplicity. Where again, we just have nearest neighbor interactions and non-periodic boundary conditions. And what they show here is, so the left plot shows you, again, the overlap as a function of the level of the binary tree. The blue line is what you would sort of expect from the Vleck Catastrophe. This is just the overlap of the tensor copies of an initial state with a final state at layer P, and you can see it decreases exponentially. Whereas if you look just at the overlap between neighboring layers of this binary tree decomposition, then this stays effectively constant. And on the right-hand side, this is to illustrate that the sufficient conditions we derived on the previous slide in terms of the spectral gap and the norm of the interaction terms is very loose in a way. Because as you can see here, the gap keeps decreasing as a function of the level of the binary tree, but the interaction strength is constant. So technically what this plot shows you is that our analysis, our perturbation theory analysis, breaks down at around level 2. But on the left-hand side, you can see that it actually still works. Like the overlap still remains constant, even though analysis breaks down. This is just to illustrate that while we do have sufficient conditions, they're very loose, and it would definitely be interesting to see if we can derive some, I guess maybe they're too strict, actually. If we can derive some looser sufficient conditions. OK, and that brings me to the conclusion. So what we did is we propose a divide and conquer strategy for preparing the ground state of n interacting quantum systems. And we show that in certain cases, our method can achieve a quasi-polynomial n scaling, in contrast to the exponential in n scaling anticipated by the Vleck Catastrophe. And of course, an open problem is, under what assumptions can we prove a poly n query complexity? Because we know that if we don't have any interactions, right? That was very early on in the talk. I showed that, well, the query complexity really should just be polynomial n, because you just prepare all the ground states in parallel and there are no interactions. So it would be nice to see how far you can push that into the interacting regime. And yeah, if you're interested and want to see more details, you can check out this preprint on the archive. And yeah, that's it. I'm happy to take questions, and thank you for your attention.
So we have time for maybe 2 questions. Yep.
Thanks for the talk. So I'm wondering if you've investigated this construction for fermionic Hamiltonians. And in that case, is there some problems you run into with anti-symmetrization if you're combining these different subsystems?
Yes, that is a very good question. So there's indeed a problem if you think about it, doing it in, say, first quantization, right? It feels like you have to constantly or actively anti-symmetrize your wave function in order to make this work. And if you have an anti-symmetrized wave function for a small subset, then it's not, and then you combine 2 subsystems, the combined wave function won't be anti-symmetrized properly. That is a very good point. And I think the best way we can think of avoiding it is to just do it in second quantization, because then it's already included in the operators, and then you won't run into any of those problems.
Yeah, there was one question here.
Thanks for the great talk. I was curious to what extent this could also work for intermediate eigenvalues in addition, or is it important that's an extremal eigenvalue?
That is a good question. I don't think this is necessary. No, I think you can also do it for intermediate ones in principle. I think it was just because, I guess, most often you're interested in ground states, but I think it should also work for intermediate ones. I don't see why not.
OK, one more question, Lynn.
Thank you for the nice talk. So is there a way to reformulate the sufficient condition in terms of some decay of correlations?
Also a good question. Probably. We haven't thought about it too much, but I would suspect so. So we have some discussion in terms of how it relates to the entanglement structure. But I think you're probably talking more about, like, say, spatial correlations, I would assume. Yeah.
The whole procedure looks very spatial.
Yes. Yeah. I think so, right? Like, because it's one condition we have on sort of where it needs to decay as a function of the level of the binary tree. You can probably rephrase in terms of like the distance with which the systems need to be separated. So I think that should be possible, but we haven't worked it out.
All right, so we'll have to stop here. Let's thank Sophia again.